Hello, my amazing students. This is Mrs. A, and we're doing 2.3, and I'm trying to get this out there. I thank you for your patience during these last couple of weeks when my dad's been in the hospital. Things have been a little bit crazy in my life, but I'm trying to get at least 2.3 and maybe 2.4 before we have our test. So 2.3, these problems are number 1 through 16 in your book, and I'm just taking a few of them. So to give you an example, so we have an f function and we have a g function, okay? And so we're going to do g composite g. We can compose a function with itself, but right here we're just evaluating for 3. So basically we can say this is the same as g of g at 3, okay? So g of g at 3 is the same thing. So what we need to do is find out what is g of 3 and then use g of 3 as the input for the g function again. All right. So g of 3, when I evaluate, I've got an x squared, okay? And x squared, when I plug in a 3, is a 9. And then I plug in a 3 here and I get a negative 2 times 3, which is a negative 6. And then I already had a minus 6. So that's 9 take away 12, which is a negative 3. So now g of 3 is a negative 3. So now I'm going to use g of a negative 3. So I'm going to plug in the negative 3. That was the output of g of 3. And then I'm going to use that for the input, negative 3, as the input to the g function again. So we already did 3. Negative 3 is going to change this none at all, because it's going to be a negative 3 squared, which will still be 9. But the negative 3 will change this one to now a positive 6. And then this one stays the same. So now the 6 and the negative 6 will cancel. I'll just have the 9. And so the answer is 9. Okay, so g composed with g of 3 is 9. And that is the correct answer. Okay, so now let's look at the second one. Now we're doing f composed with f of negative 4, which is the same as f of negative 4. So we're going to plug a negative 4 into the f function to see what this is. Okay, so we plug in a negative 4 here, and we're going to get a negative 12 plus 1, which is a negative 11. So now we're saying that's f of negative 11, and we're halfway there. So now we're going to take that f function and plug in a negative 11, which will be a negative 33 plus 1 is a negative 32. Negative 32. Okay, so look at that one. That is f of negative 4, and negative 32 is the correct answer. All right, so now let's do f composite g of negative 1, which is going to be f of g of negative 1. So we have to go to the g function and find it here and plug in a negative 1, and we're going to get negative 1 squared is 1, and then negative 2 times a negative 1 is a positive 2 minus the 6. Okay, so we evaluate that. 1 plus 2 is 3, take away 6 is a negative 3. So now we're going to put this is f of negative 3, because that's the output of the g of negative 1 in there. So now we got f of negative 3. We go over here, we plug in a negative 3. We get a negative 9 plus 1 is a negative 8. And there's all the work for that one. And that one was f of g of negative 1, which is negative 8. Okay, and lastly, g of f of negative 1. Now composition of functions is not commutative. So we have to check this one out all by itself. So g of f of negative 1 means g of f of negative 1. So we're going to come over here to the f function. We're going to plug in our negative 1. We're going to get a negative 3 plus a 1, which is a negative 2. So we're going to have g of negative 2. So now we're going to plug in our g function in negative 2. So negative 2 times negative 2 is going to be 4. And negative 2 times negative 2 is going to be 4. Take away the 6, so I have an 8. Take away the 6 is a 2. So g of negative 2 is a 2. And notice I got a different answer than I did. So f of g of negative 1 was negative 8. G of f of negative 1 was 2. They were not the same. Composition of functions is not commutative. Okay, so now I'm going to do the same thing, except I'm going to do f of g of x. Okay, so now I'm going to compose the function, and remember the f of x was 3x plus 1, and the g of x was x squared minus 2x minus 6. So we're just going to do f of g of x, not sticking a function value in. So f of g of x is the same thing as f of g of x, which means that everywhere I see an x in my original f function, I will put the whole g of x function in. So our f function is our base function. So we're going to write down 3, and instead of the x, I'm going to put a nice little parenthesis there, 3x plus 1. So there's kind of like my my skeleton of my function there. So the f function goes in there, but I take out the x, I put in my nice parenthesis, and now in the place of that parenthesis, I will put x squared minus 2x minus 6, and then I will distribute. So I'm going to get 3x squared minus 6x minus 18 plus 1. Okay, so now that the minus 18 plus the 1 is going to become a minus 17 altogether. So let's put that together. So that is the function f of g of x. All right, so now just for kicks, let's do the function g of f of x. Okay, so I'm using the same function g of f of x. I'm going to use the same two functions here. So there's my same two functions, but now I'm going to use the g function as my base function, and I'm going to substitute in the f function. So remember, my g function was the one that had the x squared in it. Okay, so my g function is right here, and I'm going to copy it down. So I'm going to have x squared minus 2x minus 6, but now when I write it, I'm going to take out the x's. I'm going to show this to you in a minute, okay? And I'm going to leave it like that. So that's my little skeleton where I took out the x's, and now in place of the x's, I'm going to put my f function. I slide the f function in. This really should have one more parenthesis, shouldn't it? Okay, so I slide the f function into these holes, and my f function was 3x plus 1. So 3x plus 1, 3x plus 1. So now I'm squaring a binomial. First term squared, product doubled, last term squared. So first term squared is 9x squared. The product is 3x. Doubled is 6x. And the last term squared is 1. And then I'm going to minus all of this. Minus 6x minus 2 times the 1 is a minus 2. Distributing that through, minus the 6. So that's my function. I just have to clean it up a little bit. I end up with a 9x squared, and the 6x and the negative 6x cancel. And then I wind up with a 1, take away an 8 is a negative 7. Now, look at what I had for my f of g of x down at the bottom, and look at what I have, same functions, g of f of x. Definitely not the same thing. All right, so now we're going to go on and do some more composed functions. Okay, so now we are doing the number 20 in your textbook. This is all on page 120, all right? And we are composing both ways and then discussing the domain. So the first thing we're going to do is talk about f composite g of x. Now let's look at the f function. The f function is actually a line, a linear function, and the domain of a linear function is all real numbers. And the g of x is a parabola, and the domain of the g of x is all real numbers. Okay, we're looking for the domain of the composed function, which should not have any restrictions. Okay, so we're going to look at it all being all real numbers, and we'll double check it after we have composed the functions together. So f composed with g is going to be, f is going to be our base function. So we're going to write our little skeleton here, 3x plus 2, minus 2. All right, so I wrote down my f function because it's my base function and it's kind of leading everything. And then I left a hole where the x was so that I can compose and stick in the g function, which is x squared plus 5. And then when I distribute this, I get 3x squared plus 15 minus 2, which is 3x squared plus 13. So f composed with g is just this function, and this function is just a parabola, and so it makes sense that the domain is all real numbers. So now we're going to take the same functions here, and we're going to do g composed with f. So g composed with f of x means that I'm going to take my g function as the base function, and that's x squared plus 5. So that's going to be x squared plus 5. I'll put my plus 5 way over here because I'm going to take out my x. I'm going to leave my square. So there's kind of the skeleton of my g function. And then into the g function, I'm going to put my f function, which is 3x minus 5. 3x minus 2. I'm reading upside down or backwards or something. 3x minus 2 is my x function that I'm going to slide into my g function. All right, so now I'm going to square this whole thing. First term squared, product doubled, last term squared. First term squared is going to be a 9x squared, and then the product is negative 6x. But when I double it, it's going to be negative 12x. And then the last term squared is going to be positive 4 plus the 5. So I simplify and I get 9x squared minus 12x plus 9 is my g of x, g of f of x, and it is also a parabola with a domain of all real numbers. So those are definitely not the same function. This was f of g. This was g of f of the same exact functions. Okay, so not the same thing at all. And that is the end of number 20. All right, so here we have problem number 30. And this is interesting because I have f of x is x to the fourth, but I have g of x is the fourth root of x. So when I'm talking about domain, the f of x function has no domain problems because it is a W shape facing upward. It is all real numbers. The g of x, however, cannot take negative x's into its little radical there. So it has a limited domain. And let's look at the composed functions because it really depends on which way we compose them. If we do f of g of x, that means we're going to use as our base function the x to the fourth. So we'll put parenthesis to the fourth, okay? And then we're going to slide in our g function which is going to be the fourth root of x. Okay, so in other words, this function is only going to be real for positive x's, and then I'm going to raise it to the fourth power, and then I'm going to get x again. All right, so f of g of x is x. However, we went through a process that required the x's to be positive only. So we would say f of g of x is x, where x is greater than or equal to 0. Okay, so in the process there was a limit right there, and we have to acknowledge that even though the function is now x, which might look like there's no limitations, the process led to this g of x had to be positive x in order to exist in the real number system. So this would be our answer, and our domain would be all non-negative x's. Okay, so now let's look at it the other way. So now our base function is going to be the fourth root of x, but we're going to take out the x, and in there we're going to put x to the fourth. Okay, now the x to the fourth is automatically going to be positive no matter what the original x is going to be, and then we would take the fourth root of that positive number. So again, we would get x, but in this case the domain would be all real. Okay, so even though we had the same two functions to start with, our domains were different because of one function being the input of the other function. So that is number 30, and I hope this is giving you an idea of how you can't really predict things until you sit down and start working about which one is the input function and which one is the output function. All right, so that's number 30. All right, so now we're doing number 36, which I wanted to do one for you that had some fractions in it because of that limiting factor of the denominator cannot go to 0. So we're going to compose both ways. Now, individually, this function would be all real numbers except for -2. This function would be all real numbers except for 0. X could not be 0. But when we compose them, okay, now let's go back to when we did that algebra of functions, which is the one before this one. So this is 2.3, that would be 2.2. When we did the algebra of functions, if we were going to multiply, add, subtract, it would be the intersection of these two domains, right? That we would call the domain of the function. But, so if I were going to add these two functions together, I would say all real numbers except x could not be 0 and x could not be 2. Okay, all real numbers but those. All right, that would work if I'm going to add the two functions together, if I'm going to subtract the two functions from each other, or if I'm going to multiply the two functions. These would be the restrictions on the domain. Okay, now if I'm going to divide the two functions, it depends on which way I divide them, because if I divide this function by this function, remember when I divide, I flip and multiply, and now x plus 2 would be in the denominator, and I'd have an additional restriction. I'd have x could not be -2 as well. Okay, so we have to be very, very careful about when we have something that flips down to the denominator. Okay, so add, subtract, multiply, divide. I would have those for add, subtract, multiply, and then I'd have to add that one in for the division restriction. Okay, but now let's see what happens with composition, because it always depends on which one is my input function. Okay, so let's do f composite g of x. We're going to do it that way first. okay, which means I'm going to take my f function as my base function, okay, and then I'm going to slide into there the g function. So I'm going to have x plus 2 over x, okay. Now, I have a little bit of complication here because I have a negative 2 hanging out over here, and I want to be able to combine these. So what I'm going to do is I'm going to multiply this negative 2 by an x over an x, okay, which is going to simplify and make it so I have a common denominator here, and I'm going to get 1 over x plus 2 over x minus 2x over x, okay, which is going to wind up being 1 over, and then since I've got the x's the same, my light went out because I'm not moving around. There we go. It's a motion sensitive light here. I'm at our classroom doing our teaching here. So now I've got to subtract, and x take away the 2x is going to be a negative x plus 2 over x. Now what happens when I divide by a fraction? I flip and multiply. So isn't this going to be equal to, ultimately, let's just put it right here, isn't that going to be equal to x over negative x plus 2? Because this bottom x is going to flip up to the top, and that would be our composed function. So, all right, we have to remember that for the two original functions to exist, I couldn't have x be 2 or negative 2, okay? Or 0. X could not be 2 or 0. But when I compose them together, x cannot be 2 because my 2 would be in the denominator. So my restrictions are going to be the same. My original functions must be defined, okay? But then I have the additional one of the g of x has got to be an input for the f of x. And so my domain would still be all real numbers except 0 and 2. Okay, so now we're going to compose that same function the other way. So we're going to do g of f of x. So let me show you the board there so you can work on copying that while I work on putting the next one on there. So now we're doing g of f of x, and we're doing the same functions. So my g function will be the base, and my g function was x plus 2 all over x. Okay, so now I'm going to take out the x, and put in my little parentheses there. Okay, and then I'm going to plug in my f function, which is 1 over x minus 2. So 1 over x minus 2, 1 over x minus 2. All right, now I'm dividing by a whole fraction there. Can I flip and multiply? So I'm going to say that's 1 over x minus 2 plus 2, which I'm going to deal with in a minute, times the reciprocal, which is x minus 2 over 1. All right, so now that I've got this, and I distribute, this whole thing over here is going to make it 1, right? So I'm going to use another board here. It's going to be equal to 1 plus, so copy that down, and then since it's just over 1, that's just going to go 2x minus 4. So this first part will become a 1, and then this to this is going to be a 2x, and this to this is a negative 4, so I wind up with that, okay, which is going to be 2x, take away 3, and that is g composed with f, which is linear, okay? And linear, we know, is all real numbers, but we also have to go back to the original function, and the original function would not have been defined if x was equal to 2. So x cannot be 2 is the restriction on that. So again, they do not look the same at all, right? This was f of g of x down here at the bottom, and this was g of f of x. They do not look the same at all. And that was the end of number 36. Okay, so this is number 42, and we are decomposing functions, which means we're taking them apart into their pieces, and we want to make it so that f composite g of x is equal to this h of x. So our task is to find out what could f be and what could g be. But the g function goes into the f function. So we could let f of x equal 1 over x. Okay, and if f of x is 1 over x, then the g of x function could be the square root of 3x plus 7. That would be one way to do it, because then when I compose them, the g of x would slide into the position where the f of x has the x. All right, that would be one way. But I could also take the f of x and let it be the square root of x. So we could say alternate. We could let f of x be 1 over the square root of x, and then g of x in this second alternative would just be 3x plus 7. Can you see how either this option or this option would both compose to give us the required function up here? Both of them would take care of that situation. So when you're doing a decomposition of functions, there are very often several different ways that you could accomplish the same task. Decomposition is a little bit more flexible. All right, so now we are decomposing number 49. And if you look at number 49, it kind of pops out at you that there's an x plus 2, an x plus 2, an x plus 2 in each parenthesis. Okay, so this decomposition is pretty easy. We're going to do f composite g is supposed to equal this function. So we're going to let f of x equal x cubed minus 5x squared plus 3x minus 1. There's a little minus 1 there. It's hard to see. And then g of x would be x plus 2. Okay, so when you did f composite g, your f of x would be your base function. You would leave a little hole where each one of the x's in, put a little parenthesis in there, and in each one of those parentheses you would stick x plus 2. And wouldn't you get the original function back again? Okay, so that was number 49. And I think we have fairly thoroughly covered all of 2.3. So we did some composing of functions, we did some decomposing of functions, and that's really all there is to 2.3. But you do need to know those thoroughly. You need to make sure that you're thinking about what domains, okay? The domain of a problem must work all the way through the problem. In other words, you have to have the domain means that the original two functions are defined, and then the composition of the two functions is also defined. So you have to add it all together to get your domain of a composed function. And your domain depends on which way you're going to compose it, whether you're going to do f of g or g of f. All right, so I hope this has helped. That means I have one more video left to do for your test material, and I'll see if I can get it done tonight. But this is Mrs. A, and may God bless your day.